Hello, this video illustrates how to represent a number, either positive or negative, using 8-bit or 16-bit or 32-bit representations. And during this video, I'll show you how negative numbers can be represented using either the 2's complement implementation or representation, or sign magnitude representation. And I'll talk about the details of each model or each representation, and show you every step of the way to convert the decimal number to its binary representation with any of these formats. So let's begin by the first example. In the first example, I want to convert 300 and negative 300 to an 8-bit binary. I'm going to use sign magnitude and 2's complement, both formats. What you will see here is that when I'll try to do that, I realize there is not enough room in 8-bit binary representation to show the number 300, because 300 is too large. Then after that, I'll show you the 16-bit representation, which is long enough that can fit a number as big as 300. Then I'll show you the 32-bit representation, and finally I'll show you the hexadecimal and octal notations for the 32-bit representation. So this is basically the outline of what I'm going to do. Let's begin by 8-bit representation. The first thing you need to do when you want to convert a decimal number like 300 to binary is to calculate every bit of it. So by bit, I mean 0 or 1. So I need to convert decimal, which is base 10, to binary base 2. The classic way of doing it is dividing by 2 and keep tracking of the remainder. So let's say divide 300 by 2, write the quotient here, write the remainder here, and do this again and again. Next row, I'll continue with 150, which is the quotient of the previous step. Divide by 2, store the quotient here, remainder here. Then the quotient becomes the next row's number. Divide by 2, store the quotient here, remainder here. After I go multiple rounds down, I will reach to this step where I get, let's say 1 here, and then the division by 2 will become the quotient of division by 2 becomes 0, and the remainder of division by 2 becomes 1, right? And then after that, the next step would be basically 0, because the quotient was 0. So 0 will give you a quotient of 0 and remainder of 0. After you calculate this whole table, then you're going to inverse this column and read it from bottom to top. I have inversed it in this column. So as you see, 0 is here, 1 is here, 0 is here, and then the rest are placed in the reverse order. After I reverse all the bits in the previous column, then I can concatenate these bits, and it gives me a binary representation for my decimal number. The binary representation begins with 0. That's basically the 2's complement representation of a positive number. It should always start with 0. And also you can consider this as the sign magnitude of a positive number. So for positive numbers, the sign magnitude and 2's complement, they both give you the same kind of representation, because when you have a positive number, the leftmost bit of both sign magnitude and 2's complement representations is called the sign. And because the number is positive, the leftmost bit must be 0. So this is basically an example of a positive number in both sign magnitude and 2's complement format. As you see, the length of this is way longer than 8. So if you count how many bits we have, the answer is 10. And this is 2 more bits, 2 bits more than the 8-bit representation. So we call that an overflow because it exceeds the maximum value you can store in an 8-bit binary, 2's complement, or in sign magnitude. Before I show you the general rule for considering a value overflow or underflow in a given representation, let me convert the positive 300 to negative 300 by applying a 2's complement operation on it, so that you know how the 2's complement representation for negative number will look like and will be calculated. Then I'm going to show you the general rule for the overflow and underflow. So this was the actual positive 300, right? This sequence of bits. If I want to make it negative 300, I have to calculate the 2's complement. 2's complement is calculated in the following way. First, you need to find the 1's complement and then the 2's complement. What is 1's complement? 1's complement is basically it means negate every bit or flip every bit of the original number. So if the bit is 0, it becomes 1. If it's 1, it becomes 0. As you see in Excel, the formula is simple. 1 minus 1 bit gives you its 1's complement or negation, or complement, I should say. And after you flip all the bits, then you're going to calculate the 2's complement, which is always equal to the 1's complement plus 1. So the concatenation of these digits or bits is the 1's complement. When you add that by 1, it's going to give you the 2's complement. When you add this number by 1, as you may know, when you're doing addition by 1 on a decimal number, you can always begin in the rightmost location and add the 1 by the rightmost digit. If there's a carry out, then you have to continue the operation with the second rightmost digit and keep going. When you concatenate these digits, these bits, the rightmost bit would be the last one. And when you add 1 with the last one, it becomes 0. Because 1 plus 1 is 2. In base 2, basically 2 is represented by 1, 0. That means you have a carry out. It's like adding 9 by 1 in base 10. When you add 9 and 1, the answer would be 10. So the sum would be 0 followed by a carry out of 1. Let me write it down this way so it would be a little bit easier for you to understand. So first, after writing the 2's complement, or 1's complement, which is basically this one, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, then that's the 1's complement of 300. Then all you need to do is to just add it by an extra 1, and the sum would be 1 plus 1 is 2. 2 in binary is represented this way, 1, 0, because basically this is the 1's bit, this is the 2's bit, and that's 2, right? So basically you have to put 0 on the sum, and then there's a carry out of 1. The carry out of 1 plus this one would be 2 again. So the sum is 0. There's another carry out 1. For the third digit, 1 plus 0 is 1, and there's no other carry out. So the rest of it would be the copy of these, which would be 0, 1, 0, 1, 1, 0, 1. So this is what I have as the 2's complement of 300. This is basically the binary representation of negative 300 in the 2's complement format. And that's basically what I have here. If you are interested in the details of this Excel sheet, the formulas are a little too complex, but you can check it out. It's not impossible to understand. You can check them out and find out how I calculated the two's complement given one's complement using Excel formulas. But in Excel, we have a lot of limitations, so it's easier to do it by hand than Excel. But I wanted to do it by Excel all the way so that you can see all numbers in a clear fashion in a nice table. For the sake of showing it in this video, there was no other reason that I used Excel for all the steps. Next thing is because again the two's complement is 10 bits. That means it cannot be fit into 8-bit representation, so it's an underflow. Why do I call it underflow? Because negative 300 is too low for the minimum possible value you can represent in 8-bit binary two's complement. So because it's too low, it's underflow. If it was too high and it was greater than the maximum value you can represent in 8-bit, it would be an overflow, like positive 300. When it's negative 300, we call it underflow. When it comes to the sign magnitude, the positive numbers would be identical to what we had in two's complement, which means you're going to begin with a 0. That's 0 here. Let me highlight it with a color, let's say with yellow. So this bit that you see here, it's basically the sign, and the rest of it is the magnitude, right? And that's exactly what I had here. So this is my sign, and the rest is my magnitude. That's the sign magnitude representation for a positive number. The sign is 0 because it's positive, and the magnitude is the rest of it, the absolute value of the number. So this is the sign magnitude of 300. As you see, it's again 10 bits. It's just like it's two's complement. And because this is overflow, this should be also overflow, because you cannot represent 300 in 8 bits. You need 10 bits at least. And then for the negative 300 in sign magnitude, which is represented as S plus M. S means sign, M means magnitude. You just need to set the sign to 1. 1 means negative, and keep the magnitude the same as what I had before for positive 300. So this part is the copy of what I had before. And the only difference is I'm going to add a 1 at the beginning. That would be my negative 300. Again, negative 300 needs 10 bits, and that's an underflow for 8-bit representation, because when the question or when you're asked to calculate an 8-bit binary representation and you cannot do that, you say this is simply an underflow. Now it's time to show you all the limits for overflow and underflow, and give you a general sense of when we have an overflow for a representation and when we have an underflow. Here are the limits I've created. The first part of this table shows you the min and max values for an unsigned number. In C, we have these unsigned types. Unsigned basically means you don't want to represent any negative numbers, so you have more room to represent positive numbers. And there are obvious examples of unsigned types in programming language like C. Java doesn't have any unsigned, but C does. The unsigned 8-bit in C is called an unsigned char. The minimum is 0, maximum is 255. Unsigned 16-bit in C is called an unsigned short. The minimum is 0, the maximum is 65,535. If you want to know where these two numbers come from, 255 is basically 2 to the power of 8 minus 1. And the maximum unsigned short is 2 to the power of 16 minus 1. For an unsigned integer, which is the most commonly used unsigned type, The minimum is 0, maximum is 4.3 billion, or to be more exact, to the power of 32 minus 1. And then the longest unsigned would be the unsigned long, which is a value between 0 and 1.8 times 10 to the power of 19. If your number that you want to represent in unsigned 8-bit exceeds 255, you have an overflow. Let's say if it's 64-bit and your number exceeds this huge number, then that would be an overflow for this unsigned 64-bit data type. The general case is when you have an n-bit representation, the min and max are going to be 0 and 2 to the power of n minus 1. So if n is, let's say, 48, you can say the maximum value is 2 to the power of 48 minus 1. We don't have a variable length integer, unsigned integer in C, so I put not applicable for this cell. Now, the rest of the table is about signed data types, which is basically the topic of this video, and all the conversions we do will be with signed data types. So I have broken this signed part into 2 subsections. The first section is the 2's complement section. The next section is the sign magnitude section. In the 2's complement section for 8-bit, which is the shortest possible signed number, the C version would be char, the regular char, not an unsigned char. And the minimum value is -128 or -2 to the power of 7. The maximum value is 127 or 2 to the power of 7 minus 1. Any value greater than 127 is considered to be an overflow for 8-bit, just like the number I showed you a few minutes ago, which was 300. Any value less than -128 is considered to be underflow, just like -300, which I showed you earlier. The 16-bit representation of 2's complement has a C equivalent, we call it short or signed short. The min value is -32,768, which is -2 to the power of 15. And the highest value or the maximum value is 32,767, which is 2 to the power of 15 minus 1. You may say, why don't we have a symmetry? For example, the absolute value of the minimum is 1 more than the absolute value of the maximum. Why is this? In 2's complement, because 0 is considered to be positive, then the real positive values would be 1 less than the real negative values, because 0 here is the border line that leans toward positive numbers. So you have 1 less positive number to show in a 2's complement representation. For 32-bit 2's complement, which is called integer in C programming language, the minimum is -2.15 billion or 2 to the power of 31 times -1. And the maximum is 2.15 billion, which is, to be more exact, it's going to be 2 to the power of 31 minus 1. When it's the long version, the min and max are going to be a little bit different. The 64-bit 2's complement has this minimum value and this maximum value. Any value less than this would be a underflow in 64-bit 2's complement representation. Any value greater than this would be an overflow. The general case is if you have an n-bit 2's complement, the minimum number you can represent is -2 to the power of n minus 1, and the maximum value you can represent is 2 to the power of n minus 1 minus 1. When it comes to sign magnitudes, we have a similar situation. The maximum values of all of these representations, 8-bit, 16-bit, 32-bit, and 64-bit sign magnitude are going to be exactly the same as what we had before for 2's complement. Because in the positive sides, sign magnitude and 2's complements are basically identical. There's no difference between them. So whatever you have for 2's complement in positive, we have the same thing for sign magnitude positive values. The only difference is for negative ones. The minimum value of let's say 8-bit sign magnitude would be negative 127, not negative 128. So it's one unit greater compared to the 2's complement. And the rest would be similar. The minimum value of the sign magnitude would be one more than the minimum value of the 2's complement one. And the reason is when you have a sign magnitude representation, there would be two zeros, one positive zero, one negative zero. And basically, if you have a complete symmetry over zero, the number of negative values would be identical to the number of positive values. So you have a 100% symmetry between negative and positive numbers in a sign magnitude representation. That's why the mean value is equal to the negation of max value when it's the sign magnitude representation or sign magnitude formatting. Let's jump back to the other tab where I was showing you the conversions. So far, I have shown you the conversion to 8-bit, which wasn't that successful because the number needed more than 8 bits. The number was too long. It was more than 8 bits. So let's think about how we can take care of this problem. The problem can be resolved by doubling, let's say, by doubling the length of the number. So instead of 8-bit, if we go with 16-bit, then you're going to have a easy time converting the decimal to binary. When you have 16-bit representation, all you need to do is to get the representation or the binary representation of a number or the binary version of the number 300 and pad it with a bunch of leading zeros so that the total length becomes 16. So far, we had 10 bits. So all I need to do is to add it or pad it with 5 more leading zeros just to get to the number that I'm looking for. This is basically this number 300 in base 16. As you saw before, we had 10 digits. And now I have, other than 10 digits, I have added 1, 2, 3, 4, 5 more zeros to get to the 16 bit representation, right? Yeah. And same is true for the sign magnitude. When you're creating a 16-bit sign magnitude representation, you need to dedicate one of the leftmost bit to the sign, and the remaining 15 bits would be the magnitude. So I need to elongate this 10-bit representation by adding 4 bits of 0 to create a 15-bit magnitude. And then there's a 0 in the leftmost side. So as you see, what I have done is, let me make this. All right. So what I have done is I have created the separation between the assignment magnitude. So this is the magnitude which has 15 digits, and I have 1 digit here for the sign. But at the end, these two, the sign magnitude and 2's complement, would have the same exact representation because the number is positive. When it comes to the negative numbers, the negative 300 is represented this way. If you compare this 16-bit representation with what we had earlier for the value of negative 300, which was the 2's complement of 300, you see that instead of adding leading zeros to make the number long enough to fill the whole 16-bit representation, we have added leading ones, and that may surprise you because you have seen leading zeros before, but you haven't seen leading ones before. So you may say, how is it possible to add leading ones? Well, if the number is written in 2's complement, and the number is negative, like in this case, negative 300, by adding leading ones, the value of the number will not change. And if you are wondering how this is possible, you can always think of the way we created a 2's complement representation. We flip all the bits. So when you have a bunch of zeros at the beginning, when you flip all the bits, zeros become 1, right? So that kind of makes sense. So remember, whenever you want to elongate the length of a positive number in 2's complement, add leading 0. Whenever you want to elongate the length of a negative number in 2's complement, you need to add leading 1s. That operation for both positive and negative numbers is called sign extension. Why do we call it sign extension? Because sign is basically the leftmost bit. When we say, let's do the sign extension, that means you're extending the sign for positive numbers, so you add leading zeros. For negative numbers, you're adding leading ones, right? And that would be your way to elongate the number and create the length that you're asked to do. For example, so for length 16, I did this. The next thing I wanted to talk about is the negative 300 sign and magnitude representation. So for the negative 300 sign and magnitude, you just use the same notation you use for 300 sign and magnitude. The only difference is instead of having a 0 in the sign, replace it with 1, and that would be it. That's going to be the negative 300 sign magnitude. So that's basically it for the 16-bit representation. Let's talk about 32-bit representation as well. Again, for 2's complement, I gotta do sign extension and add lots of zeros for the 300 and lots of ones for the negative 300 to pad the number long enough to make it 32-bit. When it comes to sign magnitude, the magnitude should be 31 bits, so you need to elongate the number, the 300, by adding leading zeros to make the magnitude equal to 31-bit long. And then the sign is 0 for positive 300, and the sign would be 1 for negative 300. And that's pretty much it. Let me also show you the hexadecimal and octal representation of these numbers. As you see here, these numbers, when they are represented with 32 bits, are pretty long, and it's very difficult for humans to read them. So the idea of hexadecimal and octal will help us shrink the size and make it easier for humans to read these 32-bit giant numbers, right? So instead of writing 32 bits or 32 sequence, like a sequence of 32 zeros and ones, we basically convert it to hexadecimal and only write down 8 hexadecimal digits, or you convert it to octal and you write only 11 digits of octal. The octal basically means base 8, hexadecimal is base 16. Binary was base 2, decimal is base 10. In decimal, we all know we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? In binary, we have 2 digits, 0 and 1. There's no other digit allowed, right? For octal, we have 8 digits, which is going to be 0, 1, 2, 3, 4, 5, 6, 7. And here is the binary values of each of those digits. For hexadecimal, we have 16 digits. From 0 to 9, we have 10 digits, which are shared between hexadecimal and decimal. From 10 to 15, we got to take advantage of the alphabetical letters. So we're going to basically use letters of alphabet to represent numbers from 10 to 15. We use letter A, which is the first in the alphabet, for number 10, B for 11, C for 12, D for 13, E for 14, and F415. And as you see, all of these 16 bits have the following binary values from full zeros to full ones, right? So every octal digit has a 3-bit binary representation, and every hexadecimal digit has a 4-bit representation in binary. In order to convert binary to hex, or in order to convert binary to octal, you got to take advantage of these two tables. This is for octal, and this is for hexadecimal. All you need to do is to break these representations. I only did it for the 2's complement. You can do it for the other one, for the sum magnitude, but it doesn't really matter. They're going to be similar. You're going to break this giant number into 4-bit pieces. For example, you say, let me use annotators. So for example, you say these 4 bits, the first 4 bits will be here. The next 4 bits will be here. And then you just break it into 4-bit pieces. Each 4 bits represents one of these rows in this table. So for example, when you do when you break your number into 4-bit pieces, the rightmost piece would be 1100, right? And that 1100, if you look at the table, is basically 12, and it's equal to C, right? So you basically say, because the last piece is 1100, the last hexadecimal digit becomes C. The one before the last 4-bit piece is 0010. That's equivalent to 2. So you basically place 2 here. Then you have 1, 0001 is 1, full zeros is 0, full zeros is 0. So how do I get this column? This column is basically the bits I had here in a line separated into 4-bit pieces, right? If you do the same thing for octal, you're going to get the octal representation. There's this small point that you need to remember here, and that is, let me annotate so you can understand it. When you want to break the number into 3-bit pieces, because let's say the representation was 32-bit and 32 is not divisible by 3, I'm gonna have a shortage of bits, because when you break 32 into 3-bit pieces, you're gonna have 10 whole 3-bit pieces plus an extra 2-bit, right? So what you need to do is to break the number, the whole 32-bit number, from right to left, not from left to right. And say these 3-bit is the last piece. We put it here, 100. Then these 3 bits is gonna be the next piece. Let me see 1 second. I think oh, sorry, I was looking at the wrong one. I'm going to convert the same number, the positive 300 to octal, not the negative 300. So I already converted positive 300 2's complement to hexadecimal. Now it's time to do the same positive 300 2's complement to octal. So let's go back to the same annotation mode. All right, so the rightmost 3 bits would be here. Then you say the next 3 bits is 101, you place it here. Then the next one would be 100, you put it here. And then after that, you have a lot of zeros. And then the last 3-bit will end here. Then after that, you don't have 3 bits, because the length of it, which is 32, is not divisible by 3. So you only have 2 more zeros, and 2 more zeros will give you the last piece, which is an incomplete piece. It's not a whole 3-piece, but that's fine. So you basically say, let's convert each single one of these pieces to an octal digit by looking them up in this table. For example, 100 is 4 because this row says so, or 101 is this one, right? So on and so forth. So after you calculate them all, you're going to concatenate all of these, and then it's going to give you the octal representation of 300 in the 32-bit 2's complement representation. So that's pretty much it. Thank you and have a good day.